Hello, ladies and gentlemen. Welcome to the JFAL conference and Project Avatar, a talk about telepresence robotics. Please welcome on stage Thomas Endres and Martin Förtsch.
Hi.
Hello.
Hi and welcome to the JFAL conference, and thanks now for the short introduction here. So welcome to our talk, Project Avatar. So it's about telepresence robotics with NAO and Kinect. So before we start with our talk, we may introduce ourselves to the audience. So Thomas.
Yeah, so my name is Thomas Endres. I studied computer sciences in Munich, and after my studies I joined TNG Technology Consulting, and then we started doing cool projects. Which of these we are talking about in a few seconds.
So cool projects. Okay.
Yeah.
So my name is Martin Förtsch, and I've studied computer sciences as well. Working for TNG. It's an IT consulting company based in Munich, and since nearly 12 years. And as Thomas already told, we are realizing crazy projects. And before we start to describe and show you our current crazy project, let's have a view back in history what we have done so far.
Yeah, it all started in the year 2013 when we were trying to control quadricopters. But back then there was only this smartphone control where you had an app and you could control it this way. We wanted something where you don't use any controller, or you just use your plain hands and no keyboard or anything like that. So you could control the quadricopter using this for left and right, forward, backward, up, down, and to control the yaw. You could do it like this. And using this gesture control, someone could control such a quadricopter within a few minutes and land it on a table, for example. So this was quite intuitive and easy to do.
Yeah. In 2015, we built a special type of augmented reality glasses. This was our Terminator vision. So we wanted to see the world through the eyes of a Terminator. And as the HoloLens at this point in time wasn't existing, we just checked what we have, which hardware do we have, and we had the development kit of an Oculus Rift available. So the idea was, why not attaching 2 RGB cameras on it, so that we can film the real environment. It gets streamed directly into the Oculus Rift, and using a special 3D camera, in this case it was the InterRealSense camera, we were able to
to add some elements to the reality,
to add graphical elements into our real world environment stream. And in this case it was you can see something like the wireframe on the face, so 78 landmark points. And we also had some kind of emotion detection, and we were also able to measure the heart rate just by looking to a person. This worked with small color changes in the skin color when blood gets pressed into the head. So, okay, the stage is falling apart. So this was the augmented reality class. So as you may already notice, our ideas, they come somehow from science fiction movies. So we had to point out, okay, what we do want to realize next. And so we had the idea, James Cameron's Avatar. So there is Jack Sully, he's disabled, he's not able to walk. And with a special system, he's able to transfer his consciousness into this blue guy. It's a Navi, it's a native living on the moon Pandora. And whilst he is in this body, he has some kind of outer body experience, and he's able to walk again somehow. And the idea was, why not trying to have an out-of-body experience as well, using off-the-shelf hardware? And this is what this talk is about. And during this talk, you will also learn some facts how to program the NAO robot, and with some live coding. For us, it was totally clear how to realize an out-of-body experience. We need some different technologies. So one is that we have to remote control an object, a robot. In this case, the decision fell on the NAO robot from Aldebaran Robotics. And as we didn't want to control the robot with a joystick or a keyboard, we thought maybe we just use a gesture camera, a 3D camera. And last but not least, of course, a special type of a head-mounted display, for example, an Oculus Rift.
Yeah, who are we, by the way? So we, that's not just the two of us. It's more people from our company who are working on this project. So we started this project like we start all of our projects at a so-called winter retreat where we go into the Alps for one day. And then we try to hack a first implementation of our project within the first day. So on day one, the gesture control was already working. The transmission of the video signal was not finished yet, but it was started. And then we continued on that. So every second and fourth Friday of a month, we continue working on such projects and tried to make it more stable and also to make it more transportable, because in the beginning it took 2 hours to build this up in a complete way.
Yeah. Okay, so let's have a look to the agenda, Thomas.
Yeah, first of all, we're going to give an introduction to Telepresence. Then we'll have a look at the history. There are quite interesting use cases there. We're going to have a look at the code and technology, which involves a live demo. We will do some live coding as well and have a look at all the technologies that were used. Then we'll have a look at the fields of application and finally the conclusion, of course.
Yes. Okay.
But let's dive right in.
Yeah, okay. So let's start with, what do you want with Telepresence robotics? So you want to overcome human barriers. One of those human barriers is the communication over long distances, like here it is shown with the picture of Frederick Remington, the smoke signal, where some natives warn each other when some enemies are coming. And in fact, there are about 4 human barriers you want to overcome with Telepresence robotics. So let's talk about dangerous places. So where a human is not able to go in without harming himself. So if you think about a power plant where a disaster beyond all expectations happened. The other 2 barriers are scaling and matter. So when it comes to scale, you just think of remote surgery and surgery robots. And so a surgeon is only able to work with the precision of, let's say, centimeters, millimeters, more millimeters, yeah. And with surgery robots, he's able to have a precision of nanometers, for example, or micrometers. And this is one of the goals of Telepresence robotics. So, Thomas, there is a difference between telerobotics and teleoperation.
Yeah, there are 2 terms now. The first one is teleoperation. And teleoperation just means that you remotely control a mechanical system. So here in the foreground we have the Carpio robot, which is another robotic system that you can control, and it is controlled by the exoskeleton in the background. So this is what teleoperation is all about. Yeah. The second term that we want to talk about is telepresence. So telepresence basically means that you feel like you are somewhere else. There are some classical fields of application, so you know all this. Probably have seen such Segway robots, especially when you've seen Big Bang Theory or something like that. And they come with a camera, they come with microphones, but they also have a display, they have loudspeakers, so that you can see the world from the distant place, but also the people at the distant place can see you in turn. And this is what telepresence is about. And telepresence robotics now combines these 2 fields. So we have teleoperation, where we control the robot, and we can see through the robot's eyes. So we feel like being in the robot's head.
Yeah. So what does it mean? Yeah, we are talking about, so in this case, multimodal telepresence. So we have two sides. We have the operator side, where the human is, who's generating a position or forces data. Usually this data gets generated by normal haptic display, so in this case a joystick, a keyboard or whatever. And this control position data gets transferred over a communication channel by your choice, and the teleoperator acts like this. And the teleoperator has some sensors attached, like for example a video camera or microphones or whatever, which sensors you have. And the teleoperator can manipulate the environment by moving objects. And using the sensors, he's able to identify those changes. And they get transferred back over the communication channel. So this is the feedback data. And the feedback data gets displayed, for example, if it's video data, you show it on a monitor. If it is some audio data, you using headphones, and so on and so on. Yeah, so what are the first projects in history doing such crazy things?
Yeah, so this is the first footage that we really found on the internet. Maybe there are earlier prototypes, but this is the first one where we found photos. So this is Ralph Mosher from General Electric in the year 1958, so this is really old. So back then he was controlling a robot. So what he has on his hands, what you see right here, is these massive devices. These are just controllers. And with these controllers, he is able to at first scare kids, so you see them in the background. But apart from that, he is also able to control the robot in the foreground. So using these devices, he was able to spin a hula hoop while doing gestures like this. But of course, this was not the main purpose of the showcase. It was its main purpose was meant to be handling dangerous substances. So you could fill one myotube into another and handle some substances like this without ever touching them. Yeah, okay.
Yeah. Let's talk about 1986, and here you can see the roof of the Chernobyl power plant, and there was a disaster beyond all expectations, and maybe you've read that. There are 500 Röntgens on the roof. So this is around about 4.66 sieverts. This means if you are there for several minutes, you are most likely to die within the next 30 days. And so here you can see a demonstration of a telepresence system. There are remote controlling a moon rover from the GDR. And there was a big problem because of the high radiation. Within several minutes, the moon rover they weren't able to control the rover anymore because the power circuits were just broken because of the radiation. Yeah, what they did was they sent so-called bio-robots or liquidators onto the roof for several seconds so that they just put away 2 shovels of this trash and to move it away from the roof. So this could be nowadays a good field of application for remote controlled telepresence stuff, which actually successfully happened around about 4 weeks ago in Fukushima. Another important telepresence example is the Lindbergh operation, which happened in 2001. So this Dr. Jacques Marusco did an operation from Europe, and he operated all the women in the USA. It was a surgery of the hips, and the good news is she survived. They had huge challenges to do because they only had a 10 megabit internet connection. So you know what it means if it comes to transferring video signals and such stuff. So now we had a look on historical applications of telepresence, and we talked about teleoperation and telepresence. And now we switch over to our showcase where we realize the full Telepresence project
using
this little guy. It's the NAO robot, and we want to talk about a little bit of this little guy. Thomas.
Yeah, so we have the SoftBank Robotics NAO robot. It was formerly built by Aldebaran, but Aldebaran was bought by SoftBank, so this is the company who now produces it. They are also producing other robots, like the Pepper robot. Or
maybe you have seen it. The Pepper robot is actually here at the conference, at the booth.
Yeah, there's one down there. And they are also producing a big version of the NAO. This is called Romeo then. So it's 1.5 meters in height then. And the advantage of this robot is that he is very cute. So, but he didn't look this cute since the start. So if you have a look at the first prototypes from the year 2005, there was just a few cables, a few servos, and some structure to keep it all together.
So it's a minimum viable product, yeah.
A minimum viable product, absolutely. And then over the time until February 2008, he got his signature shape, I would call it, and now this hasn't changed, so his appearance has stayed the same since then. But nevertheless, now has evolved. So there's been major improvements concerning things like processor power, or also the sensors, and so on and so on. So what we have right now is the Evolution 5 from the year 2014, which is the newest version that is now available. Okay.
Yeah, so this NAO robot is actually used for the World Championship of robot football. Yeah, so let's have a look to the different features we have. So we have on the head some tactile sensors. We have loudspeakers so that the NAO can communicate with us. We have cameras, 2 cameras implemented in the NAO robot. And it can run on batteries, so there is no need to have a power cord attached all the time. With the battery, it runs round about 3 to 4 hours. It depends what the robot is doing. He has some sonar sensors attached to the body, and communication works over Wi-Fi or Ethernet, as you like. And that's the most important stuff, I would say.
Quite a lot of things you can do with the robot. And there are things that are pre-programmed into the robot, and one of them is the poses. So you see here that he can go into predefined poses. Some of them are taken voluntarily, some of them are maybe not that voluntarily taken. So lying back and lying belly, he's in that position quite often. But not that you want him to be there. But the good thing is that you can get from each of these poses to each of the other poses. So the robot is able to stand up for himself once he fell down. So that's an important part of it, and he does that by performing some macros. So he has some funny macros where he tries to get up and falls down again. Yeah, okay. So these are the poses, but there is more to the robot.
Yeah. So poses are used to start a macro, so everything is somehow working autonomously then. But from time to time, you want to control each and every joint of the NAO robot. And here you can see a slide where we have all the different joints you can control of the NAO robot. So in fact, there are 26 joints, and there are somehow influenced by the human skeleton. So if you have a look onto the hips, for example, you have 3 degrees of freedom, yeah. And if you have a look to the elbow, there is only 1 degree of freedom. Yeah, and on this slide you actually can see the joint names, and they are used to move them. And this is what we are doing, wanting to do right now. So we want to do a little live coding demonstration so that you have an idea how programming the robot works. The good news is you don't have to be a robotic expert. Yeah, it's just okay if you can do some programming. So
what we want to do now is we want to put the robot into a certain position. That's why we introduced all the different joints right now. So here you can see a page from the manual. So you can see each of the degrees of freedom that the left arm has. Actually, the elbow has 2 degrees of freedom because you can also roll it around. There are a few things that we should consider right now. What we want to try to do is we want to put him from this position into this position.
So it's like
for both arms.
You have 20 seconds to comply.
Yeah, absolutely.
Okay, which movie? No! Go out. It's Robocop.
Yes. Okay, so and to do this, he's currently in this position. So we need a few degrees of freedom here. First of all, we need this one. So this would be the shoulder roll. So rolling this the shoulder upwards. Then we have the shoulder pitch, so we also need to get somehow into this position. And then we have the elbow, which needs to be controlled. So these 3 degrees of freedom are needed to get him into the necessary position. And as you can see, each of these positions can have certain values. So we can go from minus 18 degrees to plus 76 degrees, for example, for the shoulder roll. And the other ones have also certain values that they can take. And then you convert them to radians, and then this would be the values that you put into the API. Okay, so now we want to really program the robot. To do this, first of all, we have to set it up. And the setup procedure can be, it's quite easy, I would say. Because first of all, we need an application. This application needs the URL of the robot. So this is the IP, can be the IP that the robot can be reached at. So we're using Ethernet or Wi-Fi here, so it's easy to detect the robot. And then we have the port, which is normally 9559, but can be configured. And once we put in all these values into the application, then we can start the application, and then we're good to go. The next thing we need is so-called proxies. So these proxies perform operations on the robot. So there are a few proxies available. The first one would be the speech proxy, so you can let the NAO do some text-to-speech. Then there's also an audio proxy. With that you can play some WAV files or some MP3s or something like that. And then we have the posture proxy, and the posture proxy is there for getting from one predefined pose to the other predefined pose. So this is the macros I was talking about earlier. And then we have the one that we really need right now, and this is the so-called motion proxy. And this is used for controlling the joints freely. Yeah, the NAO cannot just be controlled using Java. There are also other APIs available. So, for example, you can have a Python API, or you can have a JavaScript API. So, and a C++ API. There was also a C# API, but this was discontinued. Okay, so let's go. Next slide. And this is live coding. Yeah. So Martin always has to really show that this is really live coding.
Yes, of course it is.
So this is live coding.
It won't compile, but okay, let's go.
So what we need is, of course, we need the different joints that we want to control first. And therefore, we create an array or a list, and we put in all the different joints that we need to control there. So this would be the shoulder roll, the shoulder pitch, and the elbow roll. So these 3 values that we wanted to control. We do this both for the left arm as for the right arm as well. So as you can see, The names of the joints are exactly those that we talked about in the slide where we showed all the different joints. And yeah, for the left arm, it just starts with L, and for the right arm, it just starts with R. Next, we need a few more lines, so we need another list, and we want to specify all the positions into which we want to put the robots. So for the left shoulder roll, we want to put it in position 2.0F. And for the left elbow roll, we want it to -1.5F and 0.6F for the shoulder pitch. So it's the same sequence as in the first array. And this translates to the values I was talking about 2 slides ago, where we just had this section from the manual. We do the same for the right arm, of course. So we have some values there as well. They might be a bit inverted because, yeah, it's not exactly the same for the right arm. And then, last but not least, we really want to do to move the robot. So we use the motion proxy, and there's a method called set angles. And with this method, you can then put it into this position. So we have the left joints. These are the 3 joints, and then we have the values, and the third value would be the speed with which it takes these values. So 0.0 is no speed at all, and 1.0 is the fastest it can get. And then we do the same for the right arm. Set angles is asynchronous, so it immediately returns. So what we will see when we execute this code is that it moves both hands at the same time. There are also some synchronous methods that you could use if you wanted to do something like that and then that. But yeah, let's try this as well. Okay. So now we've done everything, and we want to execute this now.
Okay, so Thomas, I'd like to have next to the robot, so just in case he will fall.
So that it doesn't fall over.
So this is live coding, so we hope everything works right now. Okay.
Sometimes it takes a little bit.
Yeah, of course.
You have 20 seconds to comply.
Okay, it's really cute if you're saying you have 20 seconds to comply. So, as you actually see, we just reached our position we wanted to have. And you can, you see it's really easy to program the robot. So the API, is really easy to use. Now we have a problem with the robot because now he stands in this position and he's really stiff. Yeah, there is voltage on the motors, and if he remains in this position till the end of the talk, I would say within the next 10 or 20 minutes he will complain, "Hey, my motors are getting too hot." So it's a good idea if we add another command, and this is the motion proxy.rest command. And so all the
You have 20 seconds to comply.
Okay, and now go to the rest. Awesome. So now the voltage is taken away from the motors, and now you can see. Awesome. So this will work. Okay. So
after we did all this live demo, now let's do another live demo, and let's go to the complete presentation of
the complete showcase. So we are demonstrating the whole showcase right now, and for this, Thomas, I ask you to take the Oculus Rift, and while Thomas is demonstrating the showcase, I will tell you what you actually see.
So what you will see right now is the showcase from the perspective of the Oculus.
Okay, so we have the Oculus Rift here. We have 2 RGB cameras attached to here. The idea is that when Thomas is wearing the Oculus Rift, he's still seeing the real environment. So Thomas, please.
Yeah, I'll put it on.
Yeah.
Okay.
Okay.
Can you take the safety off?
Yeah. Okay, awesome. Okay, so in this flight case, we have a Kinect camera. It's a 3D camera, which is able to do full body tracking. What's wrong with you?
I want to see the Kinect camera.
Okay, so we can show the audience. That's awesome. Yeah, just yeah, you can see. This is the Kinect camera. Actually, you can see those 3 dots there. So this is infrared light. The Kinect camera works with time of light, so it sends out some light photons, and they get reflected from a surface like Thomas' body, and with the how to say the face, how to say Thomas? The phase, Phasenverschiebung.
The phase shift.
The phase shift, yeah, right. We can we have a depth map, and with this, it's really easy to make full body skeleton tracking. Okay, so Thomas.
So what you see in the lower right corner of the picture is the skeleton that the Kinect camera.
Actually, you can't see that. It's dark green. So, but anyway.
Can you see it now? Yeah, okay. So,
okay.
That would be better. So what I do now is I do a circle gesture with my left hand clockwise.
Yeah. And then Thomas' consciousness...
72057594037932207 is taking over.
Okay, so now Thomas is inside the robot. You don't believe me? Hi, Thomas. How are you?
Fine.
So, and yeah, Thomas is able to control the robot. He can do some gestures here. Maybe I can give you something. Hey, be careful. Oh, that was me. Excuse me. I just crept into the Kinect, so this was...
now it will lose the person.
Yeah. Maybe you can just try it again.
I'll try it again.
Yeah. Please transfer your consciousness into the robot.
Yeah, it's not always as easy as on the first try.
Person 72057594037932339 is taking over.
Okay. So Thomas, I give you something in your hand. Please open your hands. Okay, close them. Thank you. And throw it away. Yeah. Awesome. Awesome. So this is Telepresence robotics, yeah? Okay, so but Thomas is able to walk as well. So Thomas, please make a walking gesture. Okay, stop. Okay, so, and there is another thing. We have an IoT button here, so this is... yeah, if we want to stop the project immediately, so may I ask you to push the button? Okay, awesome. So, what you have seen here is a Telepresence robotic system just based on off-the-shelf hardware. The gesture control was implemented within 1 day only. Only the other things like the video signal, transferring video signals, and so on was a challenge, and it needed some more time.
Okay.
Okay, so let's get back to the talk. So here you can see, and this maybe you can remember this slide. It was about multimodal telepresence, and now. We are showing our implementation. By the way, this slide is originally taken from the Springer Book of Robotics. So, on the operator side, as already mentioned, we are using 3D cameras. We don't care if it's a Kinect or InterRealSense, we have made both implementations. Using the 3D camera, we're generating position data, of course, which gets transferred over the communication channel. In this case, it's just Wi-Fi. The teleoperator is the NAO, who has special sensors attached. So, for example, we have a stereoscopic camera in these glasses here. So maybe you ask yourself, hey, why have you attached a stereoscopic camera if there are already 2 cameras inside the NAO? The problem is, the built-in cameras of the NAO, they are not horizontal aligned, they are vertically aligned. So it's like in Minions or something like that. And yeah, so it's quite okay if you are using the robot for playing some soccer, like for the World Championship. It's okay if this one camera here under the mouth, it's just filming downwards. That's fine. But for our project, we want to have a stereoscopic view. We needed to build this 3D printed glasses with a horizontal aligned stereoscopic camera. It's from Alibaba. It's just $30 or something like that. The camera, not the robot. This is 6,000. Okay, so so the robot is manipulating the environment and feedback data. We have different feedback data, not only the video. If you touch the NAO's head, you will feel it, because we have some vibration motors here in. So if you touch the robot, you will feel it on your head. So, you know.
That's haptic feedback, yeah.
And why? And why? Because. Okay.
Let's talk a little bit about the architecture right now. So here is all the hardware that is being used and all the different pieces of software that we use. So we have the NAO robot on the one side, and we have a laptop using the Kinect camera and the Oculus Rift on the other side. And then we have this a few other parts, like the backpack of the robot. So if you just turn him around, you can see that he has a backpack on.
I help you.
Please help me.
You're really weak.
And this is a Raspberry Pi. Model 3, and there's the camera connected to this Raspberry Pi, and then it's transmitted over Wi-Fi. So, and the last piece of hardware is an Intel IoT gateway, and this is used as the central point of communication. On the software side, we have one Kinect steerer application. So this one is just recording my skeleton and then translating that into control data for the NAO robot. Once we have that, this is sent to the Intel IoT gateway, and from there on, it's then used for the so-called NAO controller, which is using the same API, so the NAO key API that we already saw when we programmed it. And this is used for controlling the robot. The next thing that we have is the back channel. So we have the GStreamer application, which is running on the Raspberry Pi. And this one is sending all the data from the cameras, from the stereoscopic cameras, and sending this to an application called Oculus Viewer, which is implemented in SharpDX, so DirectX in this case. And it is then displayed inside of the Oculus Rift. So these are the two parts that you need. And there's the vibration controller, of course, which is extremely important and is directly using the Intel IoT gateway. Okay.
Yeah. So what if we use this rapid prototyping project on huge, large robots? Yeah, this would be awesome. So let's have a look which robots are existing in the world. So here we can see the Honda Asimo, which is built since the year 2000. And unfortunately, you can't buy this device, so this robot. There are around 60 robots existing of the Asimo. But unfortunately, you can't buy them. So you can see the robot walking upstairs and downstairs. So in this case, the robot is specialized somehow. It's a programmed routine that he is walking exactly this stairs. So if there is a slight difference, something like that can happen. Also if the motors are defect. Yeah. Don't look at this, so it's really hard to see. And why not implementing a robot which is prepared to walk on maybe slippery surfaces or stairs, whichever type of stairs it is. So this is the Boston Dynamics, the Atlas robot, for example. I'm quite sure that some of you already saw this footage. And this is the Atlas robot, and using sensors and a special kind of software, which is which uses some kind of AI and so on. He is able to walk on every surface.
It looks like he's drunk, but
it looks like he's drunk.
Not.
Maybe he is. We don't know. But he's still able to walk over slippery, wet surface, and it's amazing how good the robot hold its balance. Except if you give him a kick in the ass, then it can happen that he will fall down. But like the NAO as well, he is able to stand again, to get up again. And but still sometimes it can happen that he doesn't work as intended. Yeah. So actually, this footage was published. I don't know 4 weeks ago or something like that. We just had to show it to you, so because it looks really funny. Yeah, okay. But now let's go back to the technology of the camera, for example, in this case.
And let's talk about the 3D cameras that we used. So the first one is the Kinect camera. It was discontinued just a week ago or something like that. So, but it is, until now, it is one of the best cameras that is out there on the market for full body tracking. So what you can do with the Kinect is you normally track the skeleton of a person. So you get from if you're using the API, you get the depth image, of course, but you also get the positions of 35 points on your skeleton. So for example, you get this point or this point or this point, and using these points you can then easily translate that into movement of the robot. So you can just say, if I have this shoulder point, this elbow point and this arm point, then I can just deduct which angle this is. And we were using this extensively, and it's pretty easy since the NAO robot has similar degrees of freedom. With the Kinect, you can track up to 6 persons at the same time. And here you see a 3D visualizer using just CSS 3D transformations. So no OpenGL, no WebGL, no other things. And you can see that the Kinect is pretty precise when it comes to the positions. So even slight movements can be seen. Yeah. And I can also walk into this picture, and he will show me as a second person. So, and awesome. You can do this with up to 6 people at the same time. Okay. Yeah, so this was the Kinect, but we also used another camera. So we also tried to implement the same things with the Intel RealSense camera. There are 2 flavors of the Intel RealSense. One is somehow forward-facing, one is backward-facing. So what we have here is the F200 or SR300. So this is the forward-facing camera, and this is from the year 2014 to 2016, so these are 2 different models. And in Germany, we call this camera an egg-laying wool-milk pig, so eierlegende Wollmilchsau. So it can do pretty much everything. It is an all-rounder camera. What it can do, for example, is it can detect faces. It can detect contours of faces. It can detect your hand, the 22 points on your hand. And as you can see, this is the contours of the faces that are highlighted here. And with the RealSense camera, you also have a JavaScript API, apparently. And you can just display them here. Yeah. But this is not the only things you can do. So hand movement is also quite possible. Also recognition of faces, so it can remember your face once it's saved your the specific points of your face. It can remember you again, and it can also do something like blob tracking and so on and so on.
Yeah, actually, it looks like a Kraftwerk video.
Yeah, it does,
isn't it? Okay, so Intel just announced some new cameras based on Intel RealSense technology. So the Intel Euclid, for example. Why do we show the Euclid? Because when it comes to IoT projects or rapid prototyping projects, this camera could be interesting because it's really, really small. So if you think about the Kinect, with all the cables, cords and everything, it has a weight of around about 1.5 kilograms. So the Intel Euclid only has a weight of 100 to 200 grams. And the battery is integrated in those this USB size camera, and also the processor power, which is needed to make all those image processing and so on. Everything is inside the Euclid. It's still not yet on the market, but hopefully it will come out. So, okay, so some words to the Oculus Rift.
The Oculus Rift. So here in this project we still use the DK2 because we just had one spare part. But there's a consumer version out right now, and this is basically just a headset with a display in it. That's the main part, and it also has some gyroscopes in it so that you can see the direction and it can be tracked. But the main part is about displaying things within the VR headset. So here you can see a typical picture from the Oculus Rift, and this has two kinds of distortions in there. First of all, the picture is not a rectangle somehow, and this is called the so-called barrel distortion. So this is because it has built-in lenses, and these lenses are so close to the eye that they create some kind of distortion. And if you just calculate in this distortion, it gets eliminated again. So you can remove it by that. And the same is true if you have a look at, for example, this edge here. So this is a hard edge, but it doesn't look that hard. And this is a so-called chromatic aberration, and this is also introduced by lenses which are too close to the eye. And if you, again, calculate them in, you can remove them. And all this is done by the SDK for you, so you don't have to do this yourself. The SDK is doing this, you just have to create the scene. Okay, so what challenges did we meet? First of all, we had the limited bandwidth. So again, we have a lot of things to send over the wire. The data must be lagless, so we decided to use MJPEG compression. And with this MJPEG compression, we cannot do things like H.264 with keyframes and so on and so on. So all we can do is very simple compression, and that's why we needed more bandwidth. And what we did is we built a custom router board using two networks. One is only used for streaming, the other one is only used for the command signals.
Yeah, let's have a look onto some fields of application. So we already talked about telesurgery, where we can use Telepresence robotics. And here you can see the Da Vinci robot, which is built since 2000. And here the surgeon is able to scale all his movements so that he can not only do minimal invasive surgery, no, he can do some kind of micro or nano-invasive surgery. And another field of application. This is the Cabrio again. Here they are using an active exoskeleton, so there are some motors inside the skeleton. And here in this case, it looks like a little bit over-engineered. They are just controlling the robot in this space station, yeah. Okay. So,
another field of application would be distance learning. So this is the Vigo system. It is one of the traditional telepresence robotic system. And you can use that, for example, to go to school. It doesn't look like a use case very much, but there are people who cannot attend school. So, for example, Lyndon Beatty, he's a student in the US, and he has an immune deficiency, so he cannot attend school, and that's how he is able to still have somewhat of a social life, and he can attend class, he can talk to his classmates, and so on, which we couldn't if we didn't have this Vigo system here. And the last field of application we want to talk about is, of course, video conferencing. So this is a Kickstarter project from the year 2014, and it uses off-the-shelf hardware, so you can just put your iPad in there and then move you around the conference room and not just have a picture of your small field of view, for example.
Yeah. And actually, that's it. And maybe before we end the talk, some words to the conclusion.
Yeah. So it is possible to create a telepresence robotic system with off-the-shelf hardware in quite a small amount of time. So you just need 1 day for the gesture, and then you can build the rest in a few more days. So it is possible to create such a system with current technology, but it's not always what you want to have. So if we are talking about things like a Mars rover or something like that, you need partially autonomous systems, and for that we need different fields where we still need to be where we still need to research more. And
yeah, so we are running out of time, and thank you. We hope you enjoyed our talk, and if you like, don't hesitate to ask us outside. I don't think that we have enough time for questions and answers. Maybe one question. Do we have one question? There,
yes,
please. Yeah, Thomas, the question was, is there a Java API existing for the Kinect? And the answer is...
the problem is no, actually. So what you can do is you can get to the API by using a wrapper and putting it into a DLL, and then using that via JNI or something like that. Or you could also, and we did this, for example, for the Kinect JavaScript implementation, you could also just create an inter-process communication, like using WebSockets or using some other format. But for the example where we just saw
the visualizer,
the visualizer, this was JavaScript.
Yeah, this was JavaScript. Yeah, right.
But it was a C# API for Kinect, and then it was transmitted via WebSocket, and then we could get to the data using Java or JavaScript.
So for inter-RealSense cameras, there is a Java API existing, but it really looks ugly because it's only a very, very thin wrapper to the native libraries. So but
on our page you also have a Java implementation. No, actually it's a C# implementation of the RealSense API. But we also have we are also using wrappers for the Java implementation because it's so close to native programming with C and C++ that you somehow want to do this.
Okay, so that's it. So as I said, if you like, we will be a few more hours here at the JFall. If you like, don't hesitate to ask us. And goodbye.
Thank you.
Thank you.